All right, grade 11 chemistry. This is stoichiometry in solutions. We're going to talk about three things today. Three things are going to be making stock solutions, diluting stock solutions to make whatever solution you want, and then three-step stoichiometry using solutions. So just a lot of kind of math-based practice problems, and they're all going to be based on this formula, the C equals N over V. You think about moles per liter. Moles is N, the number of moles. V is liters, volume in liters. So concentration of something in molarity is moles per liter. We're going to be using moles per liter pretty much exclusively because it's just simpler that way. So first things first, stock solutions. Here stock is like in stock or out of stock, right? It's something that we have in the lab ready to go. So it's in stock. This is very useful in a lab. Common stock solutions are 1 molar, 0.5 molar, 0.01 molar, things like that. And in a chem lab, you'll find all kinds of them. And yeah, typically 1 molar, 0.5 molar, which is something of a known volume, very easy to measure out and use pretty much right away. To make that solution, sometimes you'll want to make it with like a powder, like something that's solid, and in that case you'll have to measure out the weight and add it to water. It's pretty easy if you're making 1 liter of solution. It'll just be whatever the grams per mole is, but if you're making other amounts it's a little bit harder, but really not that bad. So yeah, this formula is really what you're going for. Here's the volume of the solution that you're going to make, and that's the number of moles. To get the number of moles, you just use whatever mole conversion you're going for. And here's kind of how it usually works. You weigh out whatever you're using to the appropriate number. You add that to a portion of the water, to some of the water, let it dissolve, and then you fill it up to the mark. You fill it up to the mark on your flask, and then you get the exact right amount. So like we have 250 milliliter volumetric flasks in our lab, but you can see 500 milliliter ones or 1 liter ones, 1,000 milliliters, things like that. So we have a sample problem here. Let's get to our first sample problem. This sample problem asks that if I want to make 500 milliliters, so this 500 milliliter flask of a 2 molar sodium chloride solution, how much salt would I have to dissolve in my water? So if we think about that, right, we go over here, we want, I apparently don't have access to that. I'm going to pause and fix that. Okay, that fixed it. So back to this, right? Here's our stocks. Here's our question. We want to make 500 milliliters of a 2 molar sodium chloride solution. So let's write that out. We want to make 500 milliliters of 2 molar NaCl. So what we'd like to know for, the question is how much NaCl to dissolve. Now NaCl, salt, it's a solid, so we want to figure out what mass of salt to dissolve. So the kind of sub-question is how many moles? Right, how many moles? And that's where N equals C times V comes in. The number of moles is the concentration times the volume. Or put it a little bit simpler, it's 2 moles per liter. That's what the 2M stands for. 2M is 2 moles per liter. And we have 500 mils, which is 0.5 liters. So we want half a liter, and we want it to be 2 moles per liter. So if 1 liter has 2 moles, half a liter will have 1 mole. But we can do that with the formula as well. The concentration is 2 molar, actually, you know what, I'm actually going to write out moles per liter so you can see that it cancels out. Moles per liter times 0.5 liters. So the liters cancels the liters because that's technically on top. And you end up with 1 mole. 1 mole of NaCl. So we need 1 mole of NaCl. To figure out how much that weighs, we're just going to need the molar mass of NaCl. Sodium is 22.99, so sodium 22.99 grams per mole, that's just from my table. Chlorine is 35.45 grams per mole, so my total here is 58.44 grams per mole. 58.44 grams per mole. So I've got 1 mole of it, it weighs 58.44 grams per mole, so I'll multiply by the molar mass, 58.44 grams per mole, right? And that'll give me, I need 58.44 grams of salt. So I'd have to use that, I have to weigh that out on my scale and dissolve it in 500 mils. So I'll have to dissolve it in some water and then fill up the water to the 500 milliliter mark. I don't need 500 mils of water because the salt's going to take up a little bit of space. So that's why you dissolve it first and then fill it up to the line. And that's how you solve a problem like that. So that's the first thing. We've talked about making stock solutions. We made a 2 molar NaCl solution. We have 500 mils of it. If you have other volumes, you'll need different amounts. Right, so if it was 250, I'd have to use half of that mass, whatever mass we had, 58.44 grams per mole. Yeah, so now we're moving into diluting those stock solutions. So we have made a stock solution, pretend we've made a stock solution. What if we want different concentrations off of that stock solution? That's what we're getting into next. So I'm going to pause and get that set up. So diluting. Dilution is the easiest way to change concentration. You're just adding water to something to dilute it. You might have done this with something like cleaners, like bleach for cleaning, or like food coloring. It comes very concentrated. You just put a couple of drops into a lot of water and you make your food color, things like that. We're very used to diluting things in order to use them at the appropriate strength. So it's a dilution. Typically we'll go with adding the water. Like we'll have a strong stock solution. And we will add water to it because we have lots of water available. So you take a small sample of your stock solution, and then you add water until you make up to the line. There's a very simple formula here, and it relies on the fact that the N is C times V, and N is the same for both solutions. What that's saying, essentially, if we look up at the keep in mind, the number of moles of solute won't change if we're just adding water, right? We have a certain amount, like in mass, say, of salt dissolved in our water. If I add more water, I'm not changing the amount of salt, I'm just having more water in there. So the N won't change. Which means we can set up this equivalency of N1 equals N2. And we have like N1 equals C1V1, N2 equals C2V2. We set the N's equal to each other because we know they're equal to each other, and we get this expression, C1V1 equals C2V2. Concentration of the first solution times the volume of the first solution is the concentration of the second solution times the volume of the second solution. And that's the formula we're going to be using. But it's a very intuitive formula. It makes a lot of sense. You'll see when we do the practice problem that it makes a lot of sense. So here's a sample problem for that. You can see here's the general, the way to do a dilution. You pull out a certain amount of your stock solution, you put it into the new volumetric flask, and you fill it up to the mark with water, or whatever your solvent is. So that's what we're doing here. Let's say I've made my salt solution. Right? I've made my 2 molar stock solution of salt. That's what we did in that first practice question. But I want 0.35 molar salt solution, and I want 200 mils of it. The question is, number 1, how much of the stock solution should I pull into my pipette so that I add that to my new thing? And number 2 is, how much water should I add? So let's go over to the whiteboard, and we will write all of that fun stuff out. So the question is, my stock is 2 molar NaCl. 2 molar NaCl. I want 200 milliliters of 0.35 molar NaCl. Okay. So obviously I'm going to need less than 200 milliliters because this is more concentrated, 2 moles per liter, than this, 0.35 moles per liter. And how I'm going to go about this, I'm just going to go straight to the formula, is C1V1 equals C2V2. So how I do that is, I know my second one, right? I want 200 mils of 0.35. So that's my C2 and my V2. It's 2. The C2 is the concentration. So that's my 0.35 molar. 0.35 molar. And my V2 is my 200 milliliters. And I can actually leave that as milliliters. I'll show you why in a second. 200 milliliters. Now on this side, I've got C1V1. I know C1, I know 2 molar. But V1 is what I need to figure out. I want to figure out what volume of stock solution do I need. So that's going to be X. And I'm just solving this algebraic expression. 2 molar is a unit of measurement. And so X is going to stay here. I'm going to divide both sides by 2 molar. Divide that by 2 molar. And so X is going to be 0.35 molar over 2 molar times 200 milliliters. And this is why I could keep it in milliliters, because my molars are going to reduce to 1. My M's are going to reduce to 1. I'm just going to have milliliters as my final answer. My final answer is actually going to end up in milliliters. From that, it's just a calculator thing. 0.35 times 200 divided by 2. It says I need 35 milliliters of my stock. Right, 35 milliliters of stock. 35 milliliters of stock. Now there's a part B in the question. The part B in the question is how much water should I be adding to this thing? And if we think about what that means, right, I want 200 mils. I want 200 mils of this stuff. I know I'm putting 35 milliliters of stock solution. I'm going to be adding whatever 200 minus 35 is. It's 165 milliliters of water. And I'm going to add that. I'm going to add my 165 because together that makes 200 milliliters total. Okay. So that's how that kind of question works. If you're ever confused with C1V1 and C2V2, you can actually go right back to first principles, because this C2V2 is just the number of moles, and then you can work it out from there. So that's the second thing taken care of. Our last thing is 3-step stoichiometry with solutions. That takes a little bit more time to explain, so I'm glad that I have a good amount of video in order to do it with. So I'm going to pause and I'm going to get that set up. So the last thing we're doing here is stoichiometry in solutions. I'll get that away. Terrible stock image, lots of food coloring type stuff. No safety glasses either. Just awful, Anyway, we do a lot of chemistry in solutions. If you ever look at a chem lab, there is a lot of glassware and a lot of things in bottles. Typically they're just clear because a lot of solutions are clear colored. But it's because it's really easy to mix things in water. Mix 2 solutions, mix 2 liquids. It's easy to mix, it's easy to get results. You can just dry it out to get your product. Pretty simple. And we also need to be able to calculate yields for double displacement reactions, or we have 2 aqueous solutions coming in. So basically the same things that we've learned before, this 3-step stoichiometry, still apply. And importantly, the mole ratio, moles to moles, is still intact. That doesn't change anything. That just comes from the reaction, remember. It doesn't matter what the moles come in as, whether they're a liquid mole or a solid mole. It's just a number. And whatever it comes out to, a liquid mole or solid mole, it's just a number. So that doesn't matter. Mole ratio is going to stay the same. It's this part, right? It's getting to the moles of known and going from moles of unknown. Here we now have a way to do volumes. from volumes to moles. It's N equals C times V. We also have a way to convert moles back to volume, and that is V equals N over C. So it's not just mass that we can use, now we can use volume, as long as we know the concentration. We have to know the concentration. So we use the molarity to figure out how many moles, right, and then proceed as normal. And the really cool thing about this, and I keep harping on this because I think it's such an important concept, is that when we have the concentration, we don't need molar mass. We have moles per liter. We just take the volume. Something that's 2 moles per liter is 2 moles per liter no matter what solution it is. We know that there's 2 moles of that stuff in a liter. The molar mass doesn't enter into the equation, which is pretty great. You can also use it to go the other way and actually find the concentration of an unknown solution. We call that titration. That's going to be in tomorrow's lesson when we talk about acids and bases and titration. So there's going to be a little bit of acid and base math tomorrow. But it's the same kind of math that we're doing here. Just, a tiny bit more complicated. Really not that bad. So we're just going to try it out. We're just going to do 2 practice problems with 3-step stoichiometry problems that involve solutions in some way, that involve some kind of volume. And here's how it works. We start with the equation. We have to convert to moles to moles, and then back from moles to whatever we need, right? Mass, volume, concentration, whatever it's going to be. And here's our first question, our first sample problem. The question is, what volume of 0.5 molar magnesium sulfate would it take to completely react with 250 milliliters of 1 molar calcium chloride? So this is our known. We have a volume and we have a concentration. So we know that one. We can figure out how many moles there are. This is the unknown, is the volume of our 0.5 molar magnesium sulfate solution. We need to know at least one of these. We need to know either volume or concentration, and then we can work out the other one. Here's the reaction. It's just a straightforward, 1 to 1 to 1 to 1 reaction. So I'm going to go ahead and write that out on my whiteboard, and we'll proceed to actually figuring that one out. I'm feeling green for this one. Let's do green. Once again, here's our question. What volume of this stuff would it take to completely react with this stuff? And this is our known quantity. Calcium chloride is our known quantity. So let's start with that. Right, we have 250 milliliters of 1 molar calcium chloride. Right, and we want to know how many, say, milliliters of 0.5 molar magnesium sulfate do we need? So how many milliliters is our question. How many milliliters? How many milliliters? The reaction is 1 to 1 to 1 to 1. It's magnesium sulfate plus calcium chloride becomes calcium sulfate plus magnesium chloride. Right. And if we use the other way of thinking about this, this is our known. This is our known, our calcium chloride. And we have 250 milliliters of it. 250 milliliters of it, and it's 1 mole per liter. 1 mole per liter. So start with getting our moles of known, right? Moles the calcium chloride. We have 0.25, I wrote 55, 0.25 liters of it. That's the 250 milliliters. It's a quarter of a liter. I think that makes sense. Of 1 mole per liter. So if 1 liter has 1 mole, we have a quarter of a liter. Well, we just use, N equals C times V. N equals C times V. And it's getting kind of dark, so let me get some light on there. N equals C times V. Ooh, now my face is really bright. That's fine. N equals C times V. And that is 1 mole per liter times 1 mole per liter times 0.25 liters. I keep writing 55. 25 liters The liters will reduce to 1. We're just going to be left in moles. It's 0.25 moles. That should make a lot of intuitive sense now, because we have a quarter of a liter of it, 0.25 liters, and 1 liter will have 1 mole. So a quarter of a liter will have a quarter of a mole. So now we know how many moles we have. Calcium chloride. 0.25 moles of calcium chloride. All right, now to take that moles of calcium chloride, we want to turn our second step. Our step 1 is moles, figuring out the moles. Second step is figuring out the moles of our unknown, moles of magnesium sulfate. And that's using the formula. One of these takes one of these. It's a 1-to-1 ratio. So that's our, if we use our 3-step stoichiometry, I'm going to grab a blue marker here, 0.25 moles of calcium chloride times, and then the calcium chloride on the bottom, it's a 1, and magnesium sulfate on the top, that's 2. It's a 1-to-1 ratio. So clearly we're going to have the same, 0.25 moles of magnesium sulfate. 0.25 moles of magnesium sulfate. That's our second thing. I'm just going to move my face over, maybe up in the corner. All right, so I have 0. That's number 2. That's number 2. Now the last question is, how much 0.5 molar magnesium sulfate do I need? How many milliliters of 0.5 molar magnesium sulfate do I need? Well, in that case, I know I have 0.25 moles of it, and I know my concentration. I know that N is 0.25 moles. I know that C is 0.5 molar. I want V. And N equals C times V. N equals C times V. To rearrange it, V is equal to N over C. We're dividing by C. All right, we're going to divide by C. Divide by C. Divide by C. C reduces to 1. And then that's how that works. So the volume here is going to be 0.25 moles divided by 0.5 moles per liter. Moles per liter. And moles divided by moles per liter gives me liters. 0.25 divided by 0.5 is actually 0.5 liters. I need half a liter of that stuff, which should intuitively make some sense. If we go back to our initial question, right, this is twice as concentrated. It's 1 mole per liter. 1 mole per liter versus this stuff, which is 0.5 moles per liter. So if it's twice as concentrated, we need twice as much of this stuff, because this is half as strong, because it's a 1-to-1 ratio. So we kind of predict 500 mils anyway, and our answer in 3-step stoichiometry gives us 0.5 liters. So that's our first practice problem done. We're going to go to the second practice problem, which might be a little bit more palatable to you guys. Let's get to our second practice problem. Here's our second practice problem. You guys can read it. I'm going to erase the whiteboard here. Our second practice problem is, what mass of copper, so that's our unknown. Our unknown is a mass of copper. Would it take to precipitate all of the silver from 25 milliliters of 0.1 molar silver nitrate? So here we're actually going to try to solve for a mass. Our reaction is, we have 2 AgNO3 plus Cu becoming CuNO3 2 plus Ag, that's 2 Ags, plus 2 Ags. Right, and if we go back to the question, we have the known, what we know is we have 25 milliliters of 0.1 molar silver nitrate. So we'll go back over to this. We have this stuff, the silver nitrate. We have 25 milliliters of 0.1 molar silver nitrate. 5 milliliters of 0.1 molar silver nitrate. And we want to figure out this, right? How many grams How many grams of copper? So step one is moles. Moles of known. And we're going to use N equals C times V because we have concentration, we have volume. But this is in moles per liter, and this is in milliliters. So we need to convert our milliliters to liters. We divide by 1,000, 0.025 liters. Right, we divide by 1,000. Divide by 1,000 to get liters. It's 1,000 milliliters per liter, if you care. And so that's going to be concentration, 0.100 moles per liter, times, and again, this is why our unit consistency is important, times 0.025 liters. Liters are going to have to reduce the liters to 1. You want to be able to cancel liters and liters. That's why we can't be in milliliters. If you do it in milliliters, you'll end up in millimoles, which is, it's fine, but then you have to deal with millimoles. So we do that, 0.1 times 0.025 is 0.0025 moles. 0.0025 moles. Of AgNO3. Right. Note that I never had to figure out the molar mass of silver nitrate. I just had to I just had to know how many moles I made, and I had that from my liters. So I didn't need grams per mole. Even in the previous question, I didn't need grams per mole anywhere. Number 2 is the moles known to moles of unknown. That uses the mole ratio. So in this case, we start with our 0.0025 moles of silver nitrate, 0.0025 moles of AgNO3. And we're going to do that conversion factor thing. The silver nitrate goes on the bottom, because that's what we're trying to cancel. And on top is what we want, is the copper. And we put in our things. It's 2 silver nitrates for every 1 copper. So we're dividing by 2. It's going to be 0.00125 moles of copper. So that's how many moles of copper I need. It's a very small number. And then number 3 is now we go for moles of unknown to quantity. In this case, we want the mass. So we start with our 0.00125 moles of copper. And we are going to need to turn that into a mass, right? We need to turn into a mass of copper, which is what we're interested in. Now we're going to do that. We're going to go through the mole rate, to go through the moles per, the grams per mole. If I look up copper has a molar mass, I'm going to find my table here. Copper has a molar mass of 63.55. So 63.55 grams per mole. But I want moles on the bottom, and I want grams on the top because I want to be in grams when I finish. So that's the 63.55 on top. I'm multiplying by 63.55. So 63.55 times 0.00125 is 0.08. Well, 79 actually, 794, yeah, 79 grams. We'll give it two sig digs just for flavor. So that's my answer. I need 0.79. That's hard to see on the camera. 0.079. That's better. 0.079 grams of copper. So it's the same old 3-step. We get our moles of known. We have a different way of getting the moles of known, moles of the known compound. But, after that, it's the same. You got a mole ratio, and then at the end, I wanted a mass, so that's exactly the same as what we've done before. And those are the types of problems that we can do now. And that's the end of the lesson. Just to remind you, we made some stock solutions. Here's how you make a stock solution. You have to weigh something out put it in the water, and then fill it up to the line. Then we talked about diluting some stock solutions, where you take a sample of your stock solution, put it in a new flask, and you fill that up to the line to make your dilute solution that you're going to use in the lab. And then we talked about stoichiometry, 3-step stoichiometry with solutions. We just did some practice problems with that. That's it for today. We'll do some practice problems as always. And yeah, I'll see you guys in class. Thanks.